anyways. Oh, like that. Okay, it should be fine. It goes back.
Wait, didn't that just take over Blaze?
I'm
should
pretty
check
sure it
that.
did. Okay. We'll just hop over to yours real quick. Which one's yours? Just go to me. Just go to this one. Okay. And then I'll check. You can start. Start recording, and then we can. You can start.
All right, let's start. Sorry for the delay. There were a couple technical difficulties. Welcome today. Well, not today. Well, here I'm going to talk about autonomous robots, but the StuyPulse way. How StuyPulse personally works on our autonomous routines, how we build them, how we test them, and just the entire process from scratch to competitions. So let's start with a little bit of a story. So 3 years ago, I had my first taste with an autonomous routine for StuyPulse's robots. We were all remote at the time. It was the COVID era. And the software department had split up into small groups to create paths for the game challenges that year. I was working on the slalom path with a couple of friends, and the groundwork was already laid. We had a command that was able to have the robot follow a path. We just had to make that path. And these paths would be translated into tiny actions that the robot would do to traverse that path. Now, we used Pathweaver at the time, and here's a photo of Pathweaver in 2022. That's our 5-ball Auton. And Pathweaver is a piece of path generation software that provides a graphical user interface for creating paths. And it's included with WPILib, and it is great for making all of these really simple paths. I mean, you'll find it to be really simple once you start learning about it. It is one of the most powerful, I think, for tank drive primarily, path generation software for FRC, but there's also Path Planner, a tool that 3015 created about, I would say, a year and a half ago, or I think it's starting to be 2, that is able to create paths primarily focused towards holonomic drivetrains, things like mechanism drive and swerve drives. Drivetrains are able to move in an omnidirectional fashion. Now, there are a lot of paths that I have made over the years for our robots. This was Jim's 3-ball or 3-piece Auton. The one that you just saw earlier was the 5-ball, as I said. And I've also worked on some really bad stuff, like trying to balance the robot with 2 PID controllers. The person who introduced that to us is sitting in the room right now. And it appears that it took about 3 hours for him to explain it to us. And he also made a post on Chief Delphi, which everyone kind of was bullying him about. I also looked into things like Vision, using Vision last year because they were transitioning from retroreflective tape to April tags. And I was looking into using multiple cameras to track targets so that we're able to accurately determine where the robot was on the field. That didn't end well. I didn't really do anything other than read research papers about it. We were able to get some level of vision working, but in the end, we didn't really put enough effort into it, and it was a bit of a flop. So I just want to differentiate 2 things. So first, the autonomous period is the first 15 seconds, or well, normally 15 seconds, sometimes it's shorter, that the robot is in a state of autonomy during a robot match. So your robot will do things like place a cone on a peg, drive around, get mobility points, things like that. And it has to do all of this fully autonomously without human input. Now, I want to contrast this with autonomous systems, which I'll be using to refer to things like game piece indexing, where you have your robot automatically handle a game piece, whether it be a game piece that is differently colored from what your alliance is, because you don't want to score for the other alliance, right? Or getting your shooter to a correct RPM value, or having a robot arm try to traverse through your robot without breaking anything. So what StuyPulse does is we start thinking about autonomous at kickoff. So things like defining tasks. We break down the game into every single little task that the robot should be able to make or can make to play this game. So things like driving around or placing cones on pegs, the high peg, the mid peg, the low peg. Well, it's not a peg. But you know what I mean. Or like shooting a ball into the high goal versus the low goal, things like that. So here's a sample of our 2023 task list. This is basically everything that your robot could do in the 2023 game. Now, there's a lot, and we kind of was able to do everything here, I believe, other than the partners up. But yeah, so we define what tasks our robot could do so that we can design a robot around the various tasks that we decide to do. And we define various qualities that it should have. Now, once you have these tasks, you can look into them. Can you automate some of these things? Right? Our driver, if we are intaking a, why do we automate? Right? And so if your team is able to do computer vision is very helpful in automating your robot, especially in things where you have to align your drivetrain or your robot to a certain target, or know where your robot is so that you can go from point A to point B autonomously. And the next thing would be things like game piece indexing, where you just go through and you check whether this game piece should be rejected or not, whether it should stay in the robot. Especially in 2022, StuyPulse, we wanted our robot to hold 2 game pieces, right? But we also wanted the feature of rejecting game pieces from the robot. Now, instead of thinking of why don't we just shoot the ball out of the shooter at a lower RPM, we decided to make a whole entire mechanism around this fact. And so we designed a conveyor, and that required various sensors and logic trees to make good decisions about whether or not we should accept a ball, how to handle that ball, things like that. And these are things that you kind of don't want your driver to be doing because it just distracts them. The robot can do it themselves. Now, other things such as complex systems, like if you have a turret, right, you don't want your driver to be manually rotating that turret towards the goal. You just want it to automatically align, right? Or if you have arms, double jointed arms or single jointed arms, you just want them to get to a certain angle or a certain coordinate and just stay there, right? You don't want your driver to be manually adjusting the height of your arm just so that you can go, score. And so let's start with the mobility auton. This is probably the most simple auton that you can make, other than just doing nothing, although that kind of isn't really an auton. There's always or almost always a mobility point that you can get, or mobility points. I believe last year was 2 points or 3 points, something like that. And it just consists of moving your robot outside of a certain zone, whether it be the community zone last year, or whether it be those weird, like pentagons from like 2022. I don't know. But yeah, very simply, you just move your robot straight out of wherever, and especially we were thinking this could be a straight line path. We were thinking of maybe there's an alliance partner behind us, then they might want to just go straight forward to get that next ball game piece. So we just wanted to get out of the way. So that path was curved, but you can just have the robot drive straight for 3 seconds. So that's what I have here. On top is sample code for a timed robot, and on the bottom is sample code for a command-based robot. This is as simple as it gets, right? You have your drivetrain drive at a velocity of 4 meters per second at an angle. Okay, wait, what? Why did I make the angle of 180? It should be 0. But with timeout, all this code basically is saying drive at 4 meters for 3 seconds, and then stop. It'll stop. That's as simple as it gets. Anyone can be able to implement this. You can probably just copy and paste this. This might work. Probably will work. But after your mobility auton, let's look at one-piece autons. So you don't have to move in this auton. You just score the game piece that you preload onto your robot. So it might look something like autoplay. I can't tell. Your game piece manipulator, just throw out your game piece at the goal. Of course, it's the Wi-Fi. Anyways. All right. So 1.5 piece, this includes mobility, and what we call 1.5 piece autons or 0.5 piece autons are just you place down your first piece, you move, you get those mobility points, and then you go to the next game piece and you pick it up. So that is 0.5. That's the 0.5 part. You just pick it up, and then you're able to, in teleop, right, your driver will drive back to the goal and then shoot it or place it down, things like that. So here's a sample. Ignore the dock part. But that is just what a basic 1.5 piece auton looks like. You score at the green dot, you move, you grab that second game piece, and then you just stop. The next thing is an N piece auton. So that would be however many pieces you want to pick up. So say 2 pieces, 3 pieces, 4 pieces, 5 pieces, and so on. You drop your piece, you move out of the zone, you grab another game piece, and then you go back to the goal to score. All of this autonomously. And then you just rinse and repeat that cycle for the next, for the N pieces that you want to be able to get in auton. And so on the left, you'll see a 2-piece auton for our 2023 robot. And on the right, you'll see a 3-piece. So you can see that they're just building on top of each other, right? So you can kind of just copy the 2-piece, put it in the 3-piece, and add extra sections to it to start building on. Some teams even make their autons modular, in which they just have separate paths for each one, and then they just string them together. So 1-piece path, your 2-piece path, your 3-piece path, your 4-piece path, and then finally add a 5-piece path to it. And that is how you make an N-piece auton. It's very complicated. There's a lot of testing that goes into it, which we'll talk about later. But let's just talk about some special autons. So this year we had the charge station, which I guess you can call a special. Balancing on it autonomously is quite special. Like what I said earlier about the thing that took us too long, that didn't really pan out. Yeah? Oh, that was, okay. Anyway, so special autons like balancing or maybe even sometimes like hanging off of something, those are quite special. They require like extra features, things that you have to add in, functions that you have to add in. We just used our gyroscope, and then we were just like, oh, if it starts tilting back down, let's just stop the robot. It's probably going to bounce. Um, now, now that you're able to think about like what sort of autons you want, you can start building them. So what we like to do is simulate them by drawing them out. So here at kickoff, we drew out like every auton we thought. So this is a little bad because we thought we would be able to pick up two pieces at the same time in auton, but you know the the fact still stands that if you just draw them out, you simulate them. Especially, we simulated our autons with actual humans. They just like walked around like a life-size taped out field that we taped up during kickoff, and we just saw like what types of autons do we want, what can we do, and things like that. By simulating these things, you can actually better visualize everything, and you'll be able to see what's possible and like just guess what you might be able to do. And so there are some more complex systems or functions for your robot that can be automated, like turrets, game piece indexing, or falling paths. So this is kind of recycled from my previous presentation, but you first find automatable functions. That's what we've been doing for the past 15 minutes. And then we make the robot gather information from the world and from itself. And then we use that information to make decisions. Now, what this really means in terms of like actual robot features would be things like adding sensors to the robot, having computer vision on the robot to gather even more data, using state machines like for our conveyor system in 2022, and using logic trees. So let's look at Excelsior's logic tree for our indexing. You can see that we have two primary states, indexing and shooting, and there are a lot of questions that the robot asks itself before doing something. So things like, do we have an opponent ball? And all of these questions are answered by our sensors. So do we have an opponent ball? Yeah, we do. Eject that ball. If we don't have one, does the top IR sensor have a ball? If it does, we just stop because we don't want to eject our first ball. But if it doesn't, if the ball is the alliance color, then we run that motor up into the top belt, and if it's not, we should just reverse it. For the top belt, it's a little more similar. If the top iron has a ball, we just have it stop. If the ball is the alliance color, then we run. If it's reversed, well, that's like a special state. So if we want it to be reversed, then we just run in reverse. Shooting, we just shoot the ball, basically. That's what it's telling you to do. Run. Anyways, so after that, we want to translate these decisions into actions, and then these actions will lead to navigation of the robot. So the robot will start to move around based on all of these things that it has just done. Now, what comprises those two things would be things like controls algorithms from control theory. So things like motion profiling. We're ramping our inputs and our outputs. And we have a variety of controllers like feed-forward controllers, PID controllers that control things like our drivetrain or our robot arms accurately. And then we also use odometry. We grab the data that our gyroscope and our drivetrain wheels take in, and then we plug it into odometry. You can think of it as basically just a kinematics equation that calculates your robot's position based on your inputs. And then finally, path generation, which was what I showed at the beginning of the presentation, using Path Planner or Path Weaver, or just having some sort of coordinate, go from one coordinate to another that sort of system to generate paths and follow them. Now, here's the interesting part: testing them. You need to test your autonomous functions and your auton routines really rigorously. So, StuyPulse, what we do is we start with simulating our robot. In the past 2 years, we've started simulating our robot. So the benefits of doing this is you don't need a robot to actually run any of your autons or actually any of your mechanisms. In fact, you're able to visualize a robot, but not actually require a robot to run your autons. So things like simulating your drivetrain, right? You can drive around with just a picture, a moving picture, an animation of your drivetrain, so just to see if your code is working, if your math is correct, things like that. And it's just really cool to watch. WPI Lab has a couple classes. This is Field 2D. This is the field that you're able to put the robot that you're seeing move around on in glass. And then it's also in Smart Dashboard. No, it's called Shuffleboard. It's also on Shuffleboard, just under a different name, and it looks worse, in my opinion. But not only can you use Field 2D to visualize your robot on the field, you can also visualize other things like goals or targets, or like even like where your arm is on a 2D. Like if you were just looking straight down, where your arm is. You can also visualize subsystems or mechanisms with Mechanism 2Ds. So here we see 4210's robot for the 2023 season. They're actually running an auton right now, and they have on the picture of the robot, they have this green and red thing that is moving. That is a representation of their arm, right? They're just simulating this. They're simulating this. And then on the right, you'll see white lines. Those are the paths that they're taking. You'll see the robot trying to reverse those paths. And you'll also see a red line that I believe that is their vision. Or actually, no, it's not vision. I think it's the target they're looking at. Yeah. Anyways. Yeah, so any team can use these classes to visualize their robot, which can help with debugging issues with your code, just like logical issues or just, well, syntax issues, it just crashes. But, no, you can simulate your robot's logic at home instead of having to wait until you're in the lab. Finally, we have a 3D visualization, so fancy. 4099's 2023 robot. It's completing a 2-piece and dock auton right now. They're using a really neat piece of software called Advantage Scope. It's made by Jonah at Mechanical Advantage, which is being bundled into WPI Lib for the 2024 season. And it's just a really good data visualization tool. Here, they have some extra fancy stuff. They added their actual robot CAD into Advantage Scope, and you can see the mechanisms actually moving. But, you don't really need that. You just have to see that, oh, your robot's moving. And to be honest, 2D representations are fine. Now, in 2022, we were using a tank drive robot. And so we were able to use RAMIs, or these tiny robots that are just great for newbie education, or just, seeing a robot move around. We built, I think it was a 1/7 replica of the field, and it was great. I mean, we were able to run auton paths in like week 1 or 2 or something. And it was just really engaging for newbies and also just learning about autons. Is that another video? That's not going to work. You know, you don't really are like very different from the actual robot, but using an old robot to run your path is very helpful. You don't need your actual robot because you can tune paths with approximate accuracy on an old robot just to see if everything's working well, especially if you saw the alignment. Um, if you saw the alignment, that was really important just to see that working autonomously. Like you don't want it to be freaking out and driving into someone. Next, we actually got a robot. Didn't actually run like we wanted to, but you know, it doesn't really matter. Autons never work the first time. And, you know, I think it's just fun seeing a robot drive around even though it's not working properly. Here's a fun one. Robots do 3, 2, 1, enabling. Sometimes very unexpected.
Oh,
So we'll see me in
it's gonna work.
this is like I was actually sitting like right in front of where it was hitting that day, but then I decided last minute to move. I would have probably been in the hospital if that actually hit my head. But you know, sometimes you just have to work on these things constantly, and eventually it'll work. That day I think it was the most efficient day, Auton-wise. It was just 4 people, and we were able to it was a really good moral boost for the team, just seeing the robot work autonomously, just our paths. So for 2022, we tuned these for like 5 days straight or 6 days straight. Eventually, you'll get something like oh no, it would work perfectly, and then you're just annoyed. But this is all fine. I mean, it just takes a long time to get an Auton working properly. But when you get to competitions, it's not going to work perfectly. If you look at this video, you'll see, if you watch our robot, it'll load eventually.
2, 1, go!
So the robot works in all the ages. Anyways, it missed every single ball because NYC's field was a little off, very off, and so we had to tune that. So, I mean, I spent most of my first year at competitions just recording, staring at videos, at match videos, and trying to discern how much I should move one path by from like, I don't know, maybe a couple hundred pixels. It's really blurry, you know. There's like, should it be 6 inches or is it like 2 or is it, I don't know. Do I even need to change it? Sometimes it just works. But yeah, analyzing videos, and it was just fun having interactions with the people in the pit, and just talking about the robot and how we can improve it. So we talked about defining the routines that we want at kickoff, and then building the autons, spending that time building the autons, implementing them in robot code, and then testing them as much as possible so that you work out all the kinks, that it actually works, at least in your lab. You know, never actually works at competitions because autons are bad. But yeah, that's about it. I thought this presentation would be like way longer. I'm not gonna lie. Do we have any questions? Yeah, Ben. Oh, jeez. What do you mean by implement? Like, how do you draw them? Okay, so yeah, so inside of Pathfinder comes with something called Pathfinder Live. Thank God. We don't have to parse the file ourselves. But basically, that just goes through the path. I don't remember what that file looks like, to be honest. But it reads the path. It gives you a bunch of functions. They're actually changing the API for Pathfinder Live like a lot. I got really frustrated because nothing was working. And then it takes in all of these things that can like read data from your robot, so the things about ergometry, like the current module states, like if you're using Swerve Drive, and then also will take in the path, and then like two PID controllers that just try to get your robot to follow that path as accurately as possible. Those constants you have to tune yourself, which is sad. Any other questions? All right, that's kind of it. Thank you. Yeah.
I think okay.
Yeah, I believe they will be sent by email. Yeah.